Hello everybody. In this video I will talk about tangent planes. Suppose that we have a surface S, such a surface, and this surface has equation f of x, y, z equals c. Okay. And this f here has continuous first partial derivatives, and let p0 be a point on this surface. This point p0, x0, y0, z0 is a point on this surface. And now we want to find the tangent plane of this surface at point p0. To do this, first of all, I will calculate the gradient vector at p0, and all you know that the definition of the gradient vector is first partial derivative of f with respect to x times I vector plus first partial derivative with respect to y times j vector, unit vectors, and first partial derivatives with respect to z times unit k vector. Okay, this is the definition of the gradient vector, and if you if you want to calculate the gradient vector at the given point, it is enough to substitute x0, y0, z0 in these functions, because f sub x, f sub y, and f sub z are functions of x and y and z, right? So if you substitute this, then you will obtain a vector, and I will call this vector as ai plus bj plus ck. Okay, or using, if you want to use the component form, you will have a, b, and c here. Okay. Then the important point here is that all we know that if you want to calculate, if you want to obtain the equation of a plane, you need a point and you need a normal vector. For this tangent plane, this is the tangent plane here. We know what is the point, right? P0 is the point here, but we need a normal vector, and the gradient vector of this surface f at P0 is normal vector of the tangent plane. Okay, this is important. You need a point and you need a normal vector, and point is given here. It will be given in the questions or also, and the normal vector can be calculated using the function of surface and the gradient vector of this function. Okay, so this is the normal vector of the tangent plane t to the surface at the point, to the surface s at the point p0. So I know what is the point. P0 is the point x0, y0, z0. And the normal vector here is the gradient vector of f at p0, which is a, b, c. So we know that for any point p, x, y, z, because this normal vector is perpendicular to the vector p0p, we have this dot product equals 0. Gradient vector f at p0 vector dot p0p vector equals 0. This is the definition of the plane, right? So using this dot product, I have that a, b, c dot, because p is any point, it is x, y, z here, okay? So x minus x0, so there is no parentheses here, y minus y0, z minus z0 equals 0. And the dot product says that multiply first component and sum it with the multiplication of the second component, and then sum them all the first component multiplication and second component multiplication with the multiplication of third component. So I have this equation: a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. This is the equation of the tangent plane. Okay. This is the usual equation for the planes, but the which makes this equation is an equation of the tangent plane here. Those a, b, c are the components of the gradient vectors. Okay, the normal vector makes this tangent plane. Okay, also, as you can see here, we have tangent plane, but we have a normal line here also, right? This is perpendicular to that plane, so you can also find the equation of that normal line, this black line. Okay, So as you can see, this line has same direction with the normal vector, which is the gradient vector of this f at p0. So we can easily find the equation of the normal line to the surface at the point. Why? Because for a normal line, again, I need a point, and it is given as x0, y0, z0, and I need a direction vector. And we know that the direction vector of this normal line has the same direction with the gradient vector of this function at p0. So I can directly take this gradient vector as a direction vector for this line. So here I have A, B, and C components. So all we know that the parametric equation of this line can be written as x is equal to x0 plus at, right? Y equals y0 plus bt, and z equals z0 plus ct. So this is the equation of the normal line to the surface at the point p0. Okay. Okay, so let's solve some problems. Here in this problem, you want to find the equation of the tangent plane and the normal line of the surface. And the equation of surface is given with this equation, and the point is given as 0 to 12. Okay. So, all we know that in both equations, the common term is the gradient vector of the function. The function which defines the surface. So to do this, first of all, we should define f of x, y, z. And all we know that to obtain this, we need to have a constant here. So to do this, I will take that z to here, and or all those terms to this side. Then I will obtain an equation which equals to 0. So I have z minus 8 minus x squared minus y squared is equals 0. Also, you can leave this 8 here. It doesn't matter because in the calculations of the gradient vector, we will evaluate the derivatives, and the derivative of constant will be 0. Okay, you can take this 8 here also. Okay, you can define f of x, y, z as z minus x squared minus y squared equals 8. It doesn't matter. This is the second definition. I will continue with this function. So now it's time to calculate the gradient vector, and we know that gradient vector is in the first component we have the first partial derivative of f with respect to y, and here with respect to x. In the second component we have with respect to y, and the third component we have a first partial derivative with respect to z. So if you want to evaluate this derivative, you should regard z and y as constants. So here I have 0 derivative from the first derivative with respect to x. From this term I have 0 again. Here I have minus 2x, and here I have 0. So this is the first partial derivative with respect to x. And to calculate the derivative with respect to y, for this time z x will be constant for us. So I have 0, 0, 0 from the first three terms, and minus 2y from the fourth term. And if you want to calculate the first partial derivative with respect to z, for this time x and y will be constant for us. So 8 is still constant all the time. So the first partial derivative of 8 is 0, x squared is 0, y squared is 0, but the derivative of z will be 1. So this is the gradient vector of the given of the function which defines the given surface. But we need to calculate this gradient vector at the given point, right? So I have gradient vector at 0 to 12. So it says that x is 0, y is 2, z is 12. So if x is 0, first component will be 0. If y is 2, second component will be minus 4, and there is no x, y, z here, so I will directly write this as a third component there. So this is the gradient vector of the function which defines the given surface at the point 0 to 12. So it's time to find the equation of the tangent plane. And as I said, to do this I need a point, and the point is given as x0, y0, z0 is 0 to 12, and I need a normal vector. So normal vector, all we know that it is the gradient vector evaluated at p0. So this is ABC in the definition. So we have found it as 0, minus 4, and 1. So you know what is x0, y0, z0, and you know what is ABC. It's time to substitute all those numbers in this formula. 8 times x minus x0 plus b times y minus y0 plus c times z minus z0. Okay, so I will substitute it here. 8 times x minus x0 is the first part of the equation, b times y minus y0, and plus c times z minus z0 equals 0 is the formula for the tangent line. Equation of the tangent plane, sorry. So I know what is A. A is 0. 0 times x minus x0 is 0, plus b is minus 4, y minus y0 is 2, plus c is 1, and z minus z0 is 12, equals 0. From here I have 0, from here I have minus 4y plus 8, and from here I have z minus 12 equals 0. At the end, equation of the tangent plane will be this: z minus 4y equals 4. This is the equation of the tangent plane at the given points. Okay, there is a mistake in the... No, there is no mistake in the lecture notes. In the lecture notes, this equation is written as like that: minus z plus 4y plus 4 equals 0. It defines the same equation also. Okay, so let's calculate the equation of the normal line. Equation of the normal line. All we know that to evaluate an equation of a normal line, to obtain equation of a normal line, I need again a point. And we know what is the point. It is p0, x0, y0, z0 equals 0 to 12. And we need a direction vector. And direction vector is again gradient vector evaluated at p0, which is a, B, C, and it is 0, minus 4, 1. So using this, we know the parametric equation of a line. It is x is equal to x0 plus at, y is y0 plus bt, and z is z0 plus ct. Okay, so using this formula, I know what is x0a, what is y0b, and what is z0c. So I will substitute everything here. x0 is 0, 0 plus, here a is also 0, 0 times t. y0 is 2, plus I have minus 4 as b. And z0 is 12, and c is 1. 1 times t. Okay, so this is the equation of the normal line, and I can summarize it like that. X is 0, y is 2 minus 4t, and z is 12 plus t. This is the parametric equation of the normal line. Of the given surface at the point 0 to 12. Okay. Now we want to find the tangent plane to the elliptic paraboloid z equals 2x squared plus y squared at the point 1, 1, 3. Okay, we will follow the same steps. And to do this, first of all, I need to obtain the gradient vector. But the first step here is defining a function which gives our surface. And to do this, I will take z to this side for this time. You can use the other way also. You can take those terms to this side and equate it to 0. You will obtain the same result at the end. Okay. So this is our function, and I just need to calculate gradient f, and again it is f sub x, f sub y, and f sub z. The first partial derivatives of f with respect to x, y, and z. And the calculation in this first partial derivative, in the calculation I will regard y and z constants because this derivative with respect to x. So this term, derivative of this term will be 0, this term will be 0, but the derivative of this term with respect to x is 4x. Derivative of this function with respect to y. For this time, x and z will be constant, and the derivative of this term and this term will be 0, and the derivative of y squared is 2y. And at the end, if you want to calculate the first partial derivative of this function with respect to z, x and y will be constant, so the derivative of this term, this sum will be 0, 0 plus 0, and the derivative of minus z will be minus 1. So this is the gradient vector of this function, the general form. But we need to calculate this gradient at the given point to obtain the normal vector of the tangent plane and direction vector of the normal line. X is 1, y is 1, and z is 3 here. I will substitute 1 here, so I have 4. I will substitute 1 again because y is 1. We have 2. And there is no z here, so I will directly write minus 1. X, y, and z. There is no independent variable. So this is the gradient vector. Okay, now it's time to calculate equation of the tangent plane. Again, as I said, to obtain equation of a plane, you need a point, and it is given in the problem P0, x0, y0, z0 equals 1, 1, 3. And you need a normal vector, and the normal vector will be the gradient vector of this function. This function, the function defines the given surface at the given point. So it is ABC, and we have obtained that it is 4, 2, and minus 1. Okay, so we know the formula, and we just substitute everything here. Formula is that A times x minus x0 plus B times y minus y0 plus C times z minus z0 equals 0. So we have this. A is 4, 4 times x minus x0 is 1, plus b is 2, y minus y0 is 1, plus c is minus 1 times z minus z0 is 3. So we have this 4x minus 4 plus 2y minus 2 minus z plus 3 equals 0. So at the end I have this 4x plus 2y minus z. Here minus 4 minus 2 is minus 6, plus 3 will be minus 3, so I will take this to this side. So this is the equation of the tangent plane of the given surface at the given point. Okay. So let's try to obtain the equation of the normal line. Again, if you want to obtain equation of a line, you need first of all a point, and the point is given as 1, 1, and 3. And you need a direction vector And we know that the direction vector of the normal line is the gradient vector of function at given point. This is a, b, c again. So we have 4, 2, minus 1. Okay. Using this and the definition parametric equation of a line, we can obtain the equation of the normal line. And the parametric equation of a line is x is x0 plus at, y is y0 plus bt, and z is z0 plus ct. Okay, so let's substitute everything here. We know that x is x0 plus, which is 1, a is 4, 40, y is y0, which is 1, plus b is 2, 2t, and z is z0, which is 3, plus c is minus 1, t. So at the end, the equation will be this. X is 1 plus 40, the parametric equation of the normal line, y is 1 plus 2t, and z is 3 minus t. Okay. This is the equation of the tangent plane, and this is the equation of the normal parametric equations of the normal line of this surface at the given point, at the point 1, 1, 3. Okay. This is the end of this video. See you on next video.